Alright, in section 2.3 we have a few word problems that deal with the cost, revenue, and profit functions. Other types we're just going to evaluate some functions. And then toward the end we're going to look at basically the supply, that should be supply and demand curve, and where those two meet is called the equilibrium. But first of all, let's just look and go through what is the cost, revenue, and profit function and how they relate to each other, because we're going to see these things come up throughout the course. Alright, so this first example says a manufacturer has a monthly fixed cost of $100,000. So I'm going to use capital F for fixed cost. That would mean like your rent, insurance, things like that, things you have to pay every month regardless whether or not you make money or not. Alright, and then we have a production cost of $14 for each unit. So if I let X be each unit, then what we would call the variable cost would be 14 times X. So if I made one unit, it cost me $14, so it'd be $14 plus the 100,000. And so every unit I had, it would cost me $14. All right, and so then part A, what is the cost function? The cost function is defined to be your fixed cost plus any variable cost, anything money that you spend. And so since that's a function of X, I'm going to write this as 100,000 plus 14X. Right? Part B, the revenue function. How much money do you bring in? Well, this one we go back to the product sales for $20 a unit. Now remember, X is each unit. So every time you sell a unit, you make, well, you bring in $20. You don't make it, but that's your $20. So your revenue function is going to be 20 times X. And then when you're running a business, bottom line is profit. How do you make money? Profit is going to be your revenue function, how much money you bring in, minus your cost function, how much money you spent. So you could see that it could possibly be negative, meaning that you could lose money. So profit could be also a loss. So the profit function in this case would be 20x minus your cost function, and I would be careful about putting those parentheses. So I'm going to distribute, so 20x minus 14x would be 6x minus 100,000. All right, so part D asks us to compute the profit or loss corresponding to the production levels of 12,000 and 20,000 units. All right, so I'm going to say that profit, if I make 12,000, meaning let X be 12,000, so 6 times 12,000 minus 100,000. All right, so let's see, 6 times 12, that's 72,000 minus 100,000. So that would be a loss of $28,000. That's not good. All right, so then they also ask us to do it for 20,000 units. So let's see, what happens if I make more? Well, that would be 6 times 20,000 minus 100,000. And since this is positive, I actually do make a profit. So at some point I need to make more than 12,000 units to make a profit. Alright, this next example is giving us a forecast for data traffic, and this corresponds to 0 to 5, where T0 is the year 2009. Alright, so what's the total global mobile traffic in 2009? Well, again, for 2009, we let T equal to 0. Now hopefully you really don't need to write this step out, but I just want to show you where the answer is coming from, because multiplying by 0 is just so easy. And so we would get 0.06, and notice that is in million terabytes. So that's 0.06 million terabytes in the year 2009. So that's part A. So part B says, what will be the global traffic data be in 2012? All right, so let's see. If 2009 is T1, then T0. So 2012 would be T is equal to 3. So now I want to substitute in 3 every place there is an X. And at this point, definitely reach for a good scientific calculator, crank that out, and I get 1.122, again, million terabytes. So this is just showing you that you can have a model that helps you predict things in the future as far as a business is concerned. All right, so now let's see. We've got digital versus film. Some of you are probably so young you don't remember film cameras. They are still around. All right, so let's see. This would be the digital cameras being sold in millions. All right, and T is 0 in 2001. And then here we've got film cameras. So part A asks us to show that more film cameras than digital cameras were sold in 2001. So that means T is 0. So I'm just going to evaluate both functions when T is 0. And again, the math is pretty easy because you're multiplying by 0. And so we have 6.85 million digital cameras sold in 2001. And so let's look at the film cameras. And just 10 years ago, you would think that that would be more. So let's see, and certainly it is. Now, you would think that by the year 2011 we have many more digital film cameras than film ones. So let's see. Part B asks us, when did digital first exceed those of the film? So how are we going to find that out? Well, I guess we could just plug in numbers and say, oh, yep, this one's bigger. But the easiest way is, when were they equal? Once we find out what year they were equal, then we know and then we can look and say, the film ones kept growing faster. I'm sorry, the digital ones kept growing faster. So let's set these two functions equal to each other. All right, so let's see. I'm just going to add 1.85 t to both sides. And I'm going to subtract 6.85 to both sides. Again, just getting my t's on one side and numbers on the other. And so I have 4.9t equals 9.73. And yes, I am using a calculator. So I'm dividing both sides by 4.9. So t is 1.98 years. All right, so that's when they're equal. So it says, when did it? So I'm going to give it a year. So let's see, if t is 0 in 2001, so 1 year would be 2002. And since this is pretty darn close to 2 years, my answer would be that the digital exceeded those of the film in the year 2003. All right, these two problems talk about demand equations, where X represents the quantity demanded in units of 1,000, and P is the price. And again, that's going to be consistent throughout this book. So part A says sketch the demand curve. I believe on the computer homework, it's a multiple choice. You can use a graphing calculator, go to the web, there's tons of free ones. But they just want to show you, and let me back up, that this I created on a TI calculator and copied and pasted. But really, since X represents the quantity demanded, that should be greater than or equal to 0, which means none of this should be there. It really should only be this part of the graph, all right? And we certainly don't want any negative, right, because that would be a negative price. So really we're only looking at this part of what's called the parabola. So we have a domain restriction of x being greater than or equal to 0, because you don't have a zero, you don't have a negative demand. And we also would not have a negative price. Right, so determine the quantity demanded when the unit price is set at $p. Right, so you could look at the graph and come up here, but it's not very accurate. I'm just going to say, all right, since P is 7, you're solving for X. It says determine the quantity demanded. So let's see, if I subtract 16 from both sides, right? We want to get x by itself, so I'm going to divide by -1, make them both positive, and then take the square root, and remember the square root is plus or minus, but x represents what's demanded. So you can only have the positive 3, not the negative, and so since this was in units of 1,000, we would have 3,000 units demanded when the price was 7. Okay, so same thing here. We're going to look at this curve, and again, x would have to be greater than or equal to 0, and actually it even can't even be all of those numbers, but you can't have that quadrant. X can't be negative. All right, and we also don't want to have a price negative. So really you want to just confine yourself to quadrant 1. Kind of nice. All right, so let's see, P is 3. All right, so we get to do some algebra, how to get rid of a square root. We're going to square both sides. And now we have really the same type of problem we had on number 51. So I'm going to subtract 18. I'm going to divide by negative, making them positive. Take the square root. And unfortunately get the same answer, coincidental that we still have plus or minus 3, but again we can only have the positive 3, and again we have 3,000 units. So don't really worry about the graphing part on the homework. I just wanted to show you what these look like. That's not something I would test you over, but I would ask you to be able to solve for x. All right, so now we have supply equations. Okay, and again, x is the quantity supplied in units, and p is the price. So again, I have sketched these curves with a graphing calculator. So let's look at this, where x is the quantity. So x, actually, as I'm looking at this graph, I cut it off way too early because x can't be negative. It should have kept going up. But again, that's not what I'm going to test you over. I would really be concentrating on part B, determine the price at which the supplier will make 2,000 units of the commodity available. Okay, since x is in units of 1,000, I'm going to let x be 2 because I have 2,000. Right, so I just want to solve for p. So let's see, that's 4 plus 32 plus 40. If I add that together, I would get 76, and that is $76. Okay, so if I'm making 2,000 units, my price should be $76. Okay, the second graph, a little bit better. Again, we're looking when P is positive and X is positive, looking at quadrant 1. Same thing, I want to let X be 2 to determine the price, and so that would equal to $15. Okay, so now we're going to put supply and demand equations together because that is real world. When demand goes up, usually the price goes up, and when demand goes down, the price goes down, and we also have supply issues, just as you've seen in the oil industry. So we really want to determine what's called the equilibrium quantity and the price. Like, where do those match up? So the way we do that is we would set these two equations equal to each other, and where do they meet in the middle? Meaning, where does supply meet the demand? So we're going to set these two equations equal to each other, and solve for X, which would be the quantity demanded, and then solve for P, which would tell us the price. Right? So let's see. Again, since we have a quadratic, we need to set that equal to 0. So I need to move everything to, in this case, the right-hand side. Right, so that's going to be 0, right? That's a quadratic. You could use the quadratic formula, but I notice that I'm going to divide everything by 4, and if I divide this side by 4, I still get 0. And then this is very easy to factor, so I'm going to choose that method, and I'm going to set each factor equal to 0. All right, so like on problems 51 and 53, you can't have an x that's negative because it's the quantity that's demanded. They're never going to have a negative. So we have 3, and since that's in thousands, we have 3,000 units demanded. Right, so how do we determine the price? Well, you can put it in either equation because you're going to get the same answer. So I'm going to say price is 90 minus 3 times 3 squared because that was x. And if you wanted to check it out, you could also plug it into that equation. You're still going to get $63. So the equilibrium price and quantity, if you write at 3,000 demanded, you have an equilibrium price at $63. Okay, so again, this is also a supply and demand equations, and we want to find the equilibrium price and equilibrium quantity. So we're going to do exactly the same thing, a little bit nastier numbers. So set them equal to each other. I want all my x squares to be positive, so I'm going to take everything to the right-hand side. So I have 0 equals. Now, I personally don't like working with decimals like this. You could use the quadratic formula and stick it in. That would be fine. But being an old-fashioned math teacher, I'm going to go ahead and multiply everything by 1,000 because I think I missed a decimal. This should be 0.045. Since I have 3 decimal places, if I multiply by 1,000, that's going to move that decimal all the way over. So that's 45x squared plus 1,100x minus 40,000. You might be going, why would you do that? Now the numbers are atrocious. That's true. Okay, so now I'm going to divide everything by 5. Let's see if I can make these numbers any smaller. Okay, and again, I have a quadratic, just like I did to begin with. You might want to do the quadratic formula. I'm going to choose to factor it. Okay, and remember, we need only x to be a positive, so if I set this one equal to 0 and this one equal to 0, I'm going to get x to be negative 400 over 9. Can't have a negative quantity demanded. So x is 20. Now remember, that's in units of 1,000, so I have 20,000 units demanded. And so now I need the price. And again, you can use either formula. So I'm going to use this one, 0.02 times 20 squared. And again, picking up a calculator, that should be $40. So 20,000 units, I have an equilibrium price of $40.